Hi, everyone, and thank you for joining our session. I'm excited to share with you our reanalysis of fault slip rates across Southern California and the implications of our findings for the treatment of uncertainty in these data sets. Geologic slip rates measure the average rate of fault activity as recorded by offset geologic features of known age. Let's look at an example from the Death Valley Fault Zone, a slip rate site included in this study. At this site, Kurt Frankel and co-authors measured the beryllium-10 concentration in 10 surface class to determine an approximate fan age of 70,000 years. By realigning channels incised into the fan surface that had been offset across the fault, including the red point shown here, they measured a total fan offset of approximately 300 meters. These measurements indicate a slip rate of 4 millimeters per year for the Death Valley Fault Zone at this location. Slip rate measurements such as these provide constraints on fault activity over the last tens of thousands of years. These measurements are used as inputs for models of earthquake behavior and allow us to infer future earthquake hazard. We also use slip rates to connect quaternary records of faulting to models of fault zone evolution that span millions of years. Though in theory, slip rate measurements are straightforward to calculate, requiring only a measurement of offset and landform age, there are numerous challenges to communicating and comparing uncertainty across datasets. Aleatory and epistemic uncertainty contributions to these measurements can increase the width in the margin of error. Examples of aleatory or measurement uncertainty include analytical error in individual measurements of surface age, or the error in elevation models used to measure offset. Epistemic uncertainty sources are those that result from a more general lack of process knowledge, most eloquently stated as the unknown unknowns. This type of error can include production rate uncertainty in age calculations or erosional modification of offset landforms, as shown in the figure on the right. Lack of uniform reporting standards in all uncertainty types hampers our ability to make comparisons across datasets. Today, I'll be showing you how recent advances in exposure age dating, in particular process models that address sources of epistemic uncertainty, impact slip rates across Southern California. These recent updates include a mechanistic model of classed inheritance and a process model of production rate scaling. We have also assigned probability distribution functions in both age and offset to undertake a rigorous reassessment of slip rate uncertainty at 22 sites in Southern California. The location of the sites included in the study is shown in the figure on the right. I will compare published and updated slip rates in 3 ways: by the overall change in preferred slip rate value, by the overall reduction in slip rate uncertainty, and by the overlap of published and recalculated slip rate probability distribution functions. What I'll show you is that overall, slip rates do not change dramatically regionally. However, this conclusion varies depending on the metric used to assess a statistically significant change. I'm going to begin our discussion by briefly introducing cosmogenic nuclide dating. Cosmogenic nuclides, such as beryllium-10, are produced by the continuous bombardment of the Earth's surface by cosmic rays. The accrual of nuclides in the upper 2 meters of Earth's surface allows for exposure age dating over Pleistocene timescales. The measurement of beryllium-10 in quartz-rich class collected from a landform surface, as shown here on the right, is a commonly used method for determining surface age in fault slip rate studies. The resulting surface age is a function of many factors, but the 2 that we'll be discussing today are the production rate of beryllium-10 and classed inheritance. Exposure age dating using surface classed datasets is subject to bias by both inheritance and erosion. Pre-depositional accrual of a target nuclide, for example, during upstream transport, results in an inherited nuclide concentration and apparent older classed ages. On the other hand, post-depositional erosion of a landform removes material from its surface, exhuming samples that have a younger apparent age. There are no standard statistical approaches to the treatment of outliers resulting from inheritance and erosion. In this example from the Redwall Canyon fan, Frankel et al. Identified a cluster of similar ages as the true surface age and removed older outliers that had a high inherited nuclide concentration. In 2020, we published a model for class age distributions that accounts for the contribution of landslide and background erosion to the observed spread of class ages. Our model demonstrates that class age distributions can be modeled using a 3-parameter generalized Pareto distribution, or GPD. The most important of these 3 parameters for our discussion today is surface age, which corresponds to the x-axis intercept of the GPD model. We solve for the best fit GPD using a Monte Carlo Markov chain algorithm and simultaneously determine the best fit surface age. The output of this model for the Redwall Canyon dataset is shown at right. At this site, our modeling reduces uncertainty and exposure age by a factor of 3. Production rate scaling is another significant source of uncertainty in measurements of exposure age. Production rates have historically been determined by in situ measurements of cosmic ray flux at limited calibration sites and extrapolated globally using a variety of proposed scaling models. In 2014, Lifton et al. Published a method for calculating production rates by simulating the cosmic ray cascade. This model provides time-dependent nuclide-specific production rates globally and has been incorporated in the freely available Kronos Calc software package. The general impact of this update is a global reduction in production rate and a corresponding increase in exposure ages. To assess the impact of these updates to slip rates in Southern California, we apply the production rate and inheritance models to sites that measure landform age using beryllium-10 surface class datasets. Sites selected measure offset in fluvially deposited surfaces, mostly alluvial fans, and constrain surface age using 5 or more surface class. We also built probability distribution functions for offset uncertainty following the methodology of Zachar and Frankel 2009. We use 4 possible probability distribution functions for offset uncertainty, shown at right. When it was unclear what the appropriate distribution should be from the published author descriptions, we assumed a uniform distribution. I'm going to show 2 examples of how these modeling updates impact slip rates in California. The first site is the Redwall Canyon fan. At this location, we found that slip rate is reduced by more than 10% from 4.2 to 3.4 millimeters per year. We also found that the slip rate uncertainty has been reduced overall, and the overlap of the resultant slip rate PDFs, or OVC, shown at the upper right-hand side of the slide, is less than 25%. By all metrics that we use, this is a true reduction in slip rate at this location. Our second example is from the Banning Strand and the San Andreas Fault. At this site, we found that the updates we made resulted in a less than 10% change in the preferred slip rate. I want to note that the published slip rate is 3.9 millimeters per year because the authors choose to use a median value of the resulting PDF. The value I show at the upper right is 3.4 because during the modeling process, we show the maximum value of the probability distribution function. While we did not find that there was a substantial change to the preferred slip rate, we did find that there was a significant reduction in uncertainty at this location. Taking a regional view of the 22 sites included in the study, we found that our updates resulted in a 10% change in the preferred slip rate value at 14 sites in Southern California. Of these, 5 were a decrease in slip rate, and 9 represented an overall increase in slip rate. Our analysis also resulted in a reduced uncertainty at 13 of the study sites included. At 2 sites, total uncertainty remained the same, while at 7 sites, uncertainty actually increased. Increases in slip rate uncertainty at these locations is likely the result of our not including post-depositional erosion in our class age distribution model. This is a current focus of future work for us. Finally, overlap of less than 25% of the PDF area was determined at only 6 rates in Southern California. These differing conclusions highlight the importance of considering the intended application of slip rate measurements. If your analysis uses only the preferred slip rate, for example, the impact of this work could be significant. However, our recalculated slip rates overlap substantially with published rates. We do find, however, that total uncertainty is reduced overall. Today, I hope I've demonstrated to you how process models that address epistemic uncertainty and surface age dating can improve slip rate estimates. When applied across Southern California datasets, these models in general reduce slip rate uncertainty. We propose that further reductions in uncertainty can be achieved by collecting more samples at well-constrained published slip rate sites. Other talks in this session highlight opportunities for process modeling in geochronology, and as a community, we should continue seeking methods for reducing uncertainty in these datasets. Similar approaches to modeling offset uncertainty have not been adopted community-wide. Approaches to assigning offset uncertainty are generally inconsistent. Methods vary from restricting uncertainty to the sub-meter resolution of topographic data sets to more conservative estimates that encompass offset channel width and can be meters in value. Developing standards for measuring offset uncertainty would bring more consistency to our slip rate data. Our community would also benefit from adopting standards for reporting uncertainty, as has been proposed by previous authors. Finally, community repositories of slip rate data that could be rapidly updated as new models are introduced would keep our hard work up to date as the science advances. Thank you.